Welcome to the second part of this series. As you know, the last time, while making reference to a nominal pi transmission line, an equivalent circuit diagram was drawn. The equivalent circuit diagram drawn was used to derive a phasor diagram. In the same vein, we use the phasor diagram drawn to prove some mathematical formula. Finally, the mathematical formula that was derived was used to solve a medium transmission line using nominal pi method. In today's series 2, we will continue to analyze a medium transmission line using nominal pi method. So without any further ado, let's get started. Now we can continue from where we stopped the last time out, but before we start, let's look at the equivalent circuit diagram of a nominal pi line again. Looking at here, C all over 2 will now equal to Y all over 2, which is the admittance. Again, it is worth noting that the standard formula of ABCD parameters of a nominal pi line can be seen here. That is, the sending end voltage, Vs, is equal to A, multiplied by the receiving end voltage, Vr, plus B multiplied by the receiving end current, Ir, equation x1, and the sending end current, Is, equal to C, multiplied by receiving end voltage, Vr, plus the D multiplied by the receiving end current, Ir, equation x2.
To be able to prove for the standard formula, we will go back to the previous chapter again and consider equation 5, equation 4, and equation 3. Looking at equation 4 from the previous chapter, we know that the current flowing in the capacitor at the receiving end, ICR, will equal to the receiving end voltage, VR, multiplied by admittance all over 2. Now we can manipulate and substitute equation 3 into equation 4. With these, we will have this here equation 9. Again, now that we have I1, then we can substitute equation 9 into equation 5. Then we will have these here. And when further simplified, then we can say that the sending end voltage Vs is equal to open bracket 1 plus impedance times admittance all over 2 close bracket, the receiving end voltage Vr plus impedance times the receiving end current Ir, equation 10.
Now when we look at equation 10, we can see it has characteristics of AVR on the right-hand side, which is open bracket 1 plus ZY all over 2 close bracket, and BIR on the left-hand side, which is impedance Z multiplied by the receiving end current, IR. Subsequently, we can also prove for the sending end current, IS. So we will go back to the previous series again and consider equations 8 and equation 7. So take in equation 7, which is the current flowing through the capacitor at the sending end, ICS, and when further simplified will equal to sending end voltage, Vs, times admittance all over 2. Now we can substitute for the sending end voltage Vs in equation 10. When substituted, we will have this here. Now when we multiply this out, we will have this here, equation 11. Now that we have gotten the value of the current flowing through the capacitor at the sending end ICS, we can now substitute equation 9 and equation 11 into equation 8 here. When substituted, we will have this here. When further simplified, the sending end current Is will equal to this here.
Looking at the above equation there, CVR will equal to the right-hand side, while DIR will equal to the left-hand side. So we can say the matrix form can be rewritten as these here. Now we can note the following. A and D are unitless, B is measured in ohms since it is an impedance. Finally, C is measured in Siemens. For the network classification, A and D are symmetrical networks, while AD minus BC are reciprocal networks. To prove for reciprocal network, we will have these here, which is equal to 1.
Now we can solve the following question using ABCD parameter of a nominal pi transmission line. So a 3-phase 50 Hz medium transmission line has resistance, inductance, and capacitance per phase of 9 ohms, 0.16 Henry, and 0.88 microfarad respectively. It delivers a load of 40 megawatts with a voltage range of 132 kilovolts at a power factor of 0.81 lags. Determine the efficiency and regulation of the line using ABCD parameters of a nominal pi method.
To begin with, we will start by calculating for the receiving end voltage VR and the receiving end current IR. The receiving end voltage VR is equal to 132,000 divided by root 3, which is equal to 76,210.23 volts, while the receiving end current IR will be equal to 40 megawatts, all divided by 3 times 76,210.23 volts. times 0.81, all equal to 215.99 amps. And when we further consider the angle of the current, then the receiving end current is 250.99 at an angle of minus 35.90 degrees.
The impedance of the line can also be calculated. That is, impedance Z is equal to 9 plus open bracket 2 times pi times 50 times 0.16 close bracket, which equal to 9 plus J 50.26. And when converted from rectangular form to polar form, our answer is 51.05 ohms at an angle of 79.84 degrees.
Likewise, the same calculation can also be done for admittance, just that this time, instead of us considering inductance, we will be using capacitance this time around. So J2 times pi times 50 times 0.88 microfarad. With these, our answer will be 2.76 times 10 raised to power minus 4, and because we are considering the current flowing through the capacitance, then our answer will be 2.76 times 10 raised to power minus 4 at angle of 90 degrees.
Now that we have the value for impedance and admittance calculated out, we can solve for ABCD parameters. So for A parameter, it will be equal to open bracket 1 plus impedance times admittance all over 2 close bracket. When we slot our value in, then it will be 1 plus open bracket 51.05 at an angle of 79.84. Close bracket times open bracket 2.76 times 10 raised to power minus 4 at an angle of 90 degrees close bracket all over 2. When simplified, we will have this here, and when divided, it will be 1 plus 7.04 times 10 raised to power minus 3 at an angle of 169.84 degrees. However, in order to be able to add both, we will need to convert the right-hand side from polar to rectangular form. When converted, we will have this here, so when we subtract both sides, our answer will be 0.9931 plus J.0012. And when further converted from rectangular form to polar form, then our answer will be 0.9931 at an angle of 0.069 degrees. For B parameters, there is no need to calculate out for B parameter since B parameters are proved to be impedance. And again, the value of impedance is known earlier. So the answer for B parameter will be 51.05 at an angle of 79.84 degrees.
We can also calculate for the parameter C also. That is, C parameter is equal to admittance multiplied by open bracket 1 plus impedance times admittance all over 4 close brackets. When we substitute our values in, we will have this here. Now, when we multiply the polar form at the right-hand side, there we will have this here too. And when divided by 4, we will have this next. Now, in order to add this to 1, then we will need to convert from polar to rectangular form. When converted, we will have this, and we can add both. Again, before we can multiply this side of the equations to here, then we need to convert from rectangular form back to polar form again. So when we multiply both sides now, the sending end current IS will now equal to 2.75 times 10 raised to power minus 4 at an angle of 90.035 degrees. Again, we know that parameter D is equal to parameter A. That is because they both share the same formula. Hence the reason why there is no need to calculate again for parameter D.
Now that we have gotten all the values of A, B, C, and D parameters, then we can now begin to calculate for the sending end voltage Vs and the receiving end current Is. For the sending end voltage Vs, we will have the following here. When we multiply the values in polar form at both ends, then we will have this here. Again, in order to add both sides, we will have to convert from polar form to rectangular form. After conversion, then we can now add both ends now. When added, we will have this here. Again, in order to have our final answer in polar form, then we will have to convert from rectangular form to polar form again. When converted, the sending end voltage will now be 83,982.017 at an angle of 5.28 degrees.
In the same vein, too, we can also calculate for the sending end current, IS. With these, we will have these here. So when we multiply the polar form at both sides, we will have these here. Again, before we can add both sides, we will have to convert from polar form to rectangular form. So we can now add both sides now. When added, we will have this here. And when converted back to polar form, the sending end current will be 202.91 amperes at an angle of minus 31.2 degrees.
Now that virtually all the values we need are all gotten, then we can calculate for the voltage regulation of the line and also the line regulations. For the voltage regulation of the line, the receiving end voltage at no load minus the receiving end voltage at full load all over the receiving end voltage at full load times 100. However, since we don't have the value of no load, then we can do this. That is the sending end voltage, Vs, all over parameter A minus the absolute of the receiving end voltage, Vr, all over the absolute of the receiving end voltage, Vr times 100. When we substitute our values in, we will be having these here, which will further be equal to 10.96%.
Finally, the efficiency of the line can also be calculated out also. So the power at the receiving end all over the sending end power times 100. But before we can proceed with our calculations, then we will need to calculate the phase angle, which is the algebraic sum of both the sending end voltage angle and the sending end current angles. So when we add both angles here, we will be having an angle of 36.3 degrees, and the cos of 36.3 is 0.80 lags. Now that we have known our combined phase angle for voltage and current, so we can calculate for the sending end power, which will be 40.89 megawatts. So we can now calculate for our line efficiency, which will be 97.80%. And that is it for today's series. In the incoming series, we will be analyzing long transmission lines using exact and rigorous methods. Until then, peace.